Welcome to The Sleepy Scholar. It's lovely to have you here tonight. Wherever you are right now, settle in. Maybe you're under a heavy blanket with just one lamp still glowing in the corner. Maybe you're on a couch or a train rocking gently through the dark, or curled on your side with your eyes already half closed. It doesn't matter where you are. You found your way here, and that's enough. So let yourself sink a little deeper into wherever you're lying, and let your shoulders come down from wherever they've been hiding all day. Before we begin, I have a small thing to ask, and I'll keep it gentle because nothing here is meant to ask much of you. If you enjoy these slow journeys into quiet corners of the night, a like and a subscribe really does help this sleepy little channel keep going. Small creators like me rely on that more than you'd think. And to everyone already here, already part of this, thank you, truly. You make these nights possible. So while you're drifting, if you feel like it, let me know. Where in the world are you watching from tonight? What time is it in your corner of the dark? I love imagining all of you scattered across the planet, all of us lying still under the same sky, all of us spinning quietly through the same slow galaxy. We'll come back to that thought later. For now, just hold it loosely. And here's my promise to you. We're going to move slowly tonight. There is no hurry, none at all. I'm not going to ask you to concentrate or to remember anything or to follow every turn. If your eyes close before we're done, that's perfectly fine. The galaxy will still be turning when you wake. The ideas will still be here. You can come back to them another night or never. And either way, you'll have lost nothing. This isn't a lecture. It's more like a long, soft walk through one beautiful idea, and you're welcome to fall asleep partway down the path. I'll keep walking quietly either way. I should warn you in the friendliest way that tonight's subject is genuinely lovely, and I'll do my best not to make it so interesting that it keeps you awake. But if it does, well, at least you'll drift off knowing something true and strange about the sky above your roof. A fair trade, I think. So, let's begin, shall we? Softly. Tonight we're going to wonder about something that almost nobody stops to wonder about, even though it's hanging right there in every picture of a galaxy you've ever seen. Those great glowing pinwheels, those graceful curving arms of light, sweeping out from a bright center like cream stirred slowly into coffee, like the spokes of some impossibly grand and gentle wheel. A spiral galaxy. You know the shape. You've seen it on posters and in textbooks, and on the backs of cereal boxes probably. It's one of the most familiar images in all of science and one of the most beautiful. And here is the quiet question we're going to follow all the way down, slowly, tonight. How does a spiral galaxy keep its shape? It sounds simple, doesn't it? Almost too simple to bother asking. The galaxy is spiral-shaped, so it stays spiral-shaped, and that's that. But hold on with me a moment, because hidden inside that lazy little question is one of the loveliest puzzles in all of astronomy. A puzzle that, once you really see it, will quietly refuse to let you go. The kind of puzzle that ends with a gentle, "oh," somewhere in your chest. We'll get there. No rush. We have all night. But to feel the puzzle properly, we have to start somewhere much closer to home. We have to start with how slowly, how grandly, how patiently everything up there is actually moving, because the sky looks so still, doesn't it? You can lie out in a field on a summer night, and the stars seem nailed in place. Fixed, eternal, painted onto the dark, but they're not still at all. Nothing up there is still. Everything is turning, including us, including you, lying right where you are. Let's start with our own star, the Sun. Our Sun is not sitting in the middle of the galaxy. It's out in the suburbs, you might say. It sits roughly 27,000 light-years from the center of the Milky Way. Now, a light-year is already a number so big it's hard to hold in your head, so let's not even try to hold it. Just let it be enormous. A light-year is how far light travels in a whole year, moving faster than anything in the universe, and our Sun is 27,000 of those distances out from the heart of it all. Far, wonderfully, dizzyingly far. We live a long, long way from downtown. And out here in the quiet suburbs of the galaxy, the Sun is moving. It's drifting in an enormous, slow circle around that distant center, carrying us and all the planets along with it. We are, all of us, on the longest, gentlest carousel imaginable, turning forever around a center we will never reach. So how long does one trip around take? How long is one lap of the Sun around the whole galaxy? Here is the number, and I want you to let it wash over you slowly, the way you'd let warm water wash over your hands. One trip takes the Sun somewhere between 225 and 250 million years. 225 million years for a single loop. Astronomers have a name for that span, and it's a lovely one. They call it a galactic year. One galactic year, one single time around. Just sit with that for a breath. 225 million years for one turn. The Earth itself, the whole planet beneath you, has only existed for about 4.5 billion years, which means that since the Earth first formed, since it cooled from a ball of molten rock into a world with oceans and continents, and eventually you, in all that unimaginable stretch of time, the Sun has only gone around the galaxy about 20 times, 20 laps, that's all. Think about how slow that is. Think about everything that has happened in a single one of those laps. The last time the Sun was in roughly the position it's in now, the dinosaurs were just beginning their long reign. The continents wore different shapes. There were no flowers yet of the kind you'd recognize, no grass as we know it. An entire age of the Earth, the whole rise and fall of the great reptiles, then the slow climb of the mammals, then the appearance of the first humans, then everything humans have ever done, every empire, every song, every person who has ever lived and loved and looked up at the sky, all of that, all of it, fits inside a fraction of one single lap of the Sun around the galaxy. We have not even finished one turn since the first humans walked the Earth, not even close. So when I say the galaxy is moving slowly, I want you to feel how vast that slowness is. It's not lazy slowness, it's not the slowness of something tired, it's the slowness of something so enormous that even moving at unthinkable speeds, it takes 250 million years just to come back around. There is a deep peace in that, I think. A reminder that some clocks tick so slowly that all of human history is barely a single chime. Whatever kept you up tonight, whatever weighed on you today, out there, none of it has even registered. The galaxy hasn't moved enough to notice. There's something restful in being that small inside something that patient. So let that settle. The Sun, 27,000 light-years out, turning once every 200-some million years. About 20 trips in the entire life of the Earth. A galactic year, slow and grand and gentle. But now, and here's where the lovely puzzle begins to wake up. Now we have to notice something. The Sun is not the only thing going around. Every star in the galaxy is going around that same center. Hundreds of billions of stars, all turning, all orbiting, all caught on their own enormous carousels. And here is the crucial thing, the small fact that the whole mystery rests upon. They do not all go around at the same speed. This is the heart of it, so let me say it slowly and softly, and we'll build a little picture together. The stars near the center of the galaxy, the ones close in to the heart of it, complete their loops much, much faster than the stars far out in the suburbs like our sun. The inner stars whip around in a relatively short time. The outer stars take far longer to make their longer, lazier loops. Stars at different distances from the center turn at different speeds. Astronomers have a name for this too, and it's worth knowing just so the picture sits clearly in your mind. They call it differential rotation. Differential meaning different. Different parts rotate at different rates. The whole disk does not turn as one solid piece. Now that might sound abstract, so let me give you something to picture, something you can almost feel in your hands. Imagine you're stirring a cup of coffee. You've just poured in a little cream, and you give it a slow stir with your spoon. Watch what happens to the cream. Near the center where you're stirring, the coffee moves fast, and the cream there races around. Out near the rim of the cup, the coffee turns much more slowly. The whole surface isn't turning as a single solid sheet. The middle is outrunning the edge. That's differential rotation, right there in your morning cup. The inside spins faster than the outside. Or picture a different thing. Picture runners on a great circular track. Not a normal track, but one where everyone has to complete a full circle around the same center point. The runner on the innermost lane has a tiny circle to run, so they come around again and again quickly. The runner way out on the outermost lane has an enormous circle to cover, so even running their hardest, they take much longer to come all the way around. Start them side by side in a neat straight line pointing out from the center. And what happens? Within a lap or two, the inner runner has lapped ahead, the outer runner has fallen behind, and that neat, straight line you started with, it's gone. It's smeared into a curve, then a tighter curve, then a hopeless tangle. The line cannot stay a line. The faster inside drags ahead of the slower outside, always, relentlessly. That's a galaxy. The inner stars race ahead. The outer stars lag behind. Differential rotation, turning forever. Now hold both of those pictures gently in your mind. The coffee, the runners, because we're about to walk straight into the puzzle that has been waiting for us this whole time. And it's a beautiful one. It's the kind of thing that once you see it, you can't quite unsee. Here it is. Here is the load-bearing mystery of the entire night. If the spiral arms of a galaxy were made of fixed stars, if an arm were just a line of particular stars, like beads on a string, or like spokes painted onto a wheel, then differential rotation would destroy it. Quickly. Think it through with me, slowly. The part of the arm near the center is racing around fast. The part of the arm far out in the suburbs is lagging far behind. So the inner part of the arm pulls ahead, and the outer part trails, and the arm gets wound up, tighter and tighter and tighter, just like that line of runners smearing into a curve. Wind, wind, wind. The spiral would coil up on itself like a watch spring being cranked too far, and it wouldn't take long. Not on the scale of galaxies. Within just a few rotations, it did a few 100 million years, which sounds like forever, but is barely a fraction of the galaxy's life. The arms would be wound up so tightly that they'd smear out completely. The lovely open spiral would blur into a featureless, indistinct disk. Just a smudge of light, all the structure churned away. The arms would simply cease to exist as anything you could point to. That's what should happen. That's what the simple picture demands. If the arms are solid lines of stars, they wind up and vanish in a cosmic eye blink. And yet, when we look out at the universe, we see spiral galaxies everywhere. Beautiful, open, graceful spirals. And here's the thing that should make your sleepy mind go quiet for a moment. We see them in galaxies that are billions of years old, not a few 100 million, billions. These galaxies have been turning for 10 times, 20 times, 100 times longer than it should take to wind their arms into oblivion. The arms should have smeared away into nothing an unthinkably long time ago. They should be gone. Wound up, blurred out, finished. But there they are, crisp and clear and open, spiraling exactly as they should not be able to. Do you feel it? That gentle wrongness, that little snag in the logic. The galaxy is doing something it has no right to do. The math says the arms must wind up and disappear. The sky says they don't. Something is keeping those arms open across spans of time, so vast they make a galactic year look quick. Something is holding the shape against the relentless smearing of differential rotation. And that something, what it actually is one of the most quietly astonishing answers in all of science. It overturns the most natural assumption you could possibly make about what a spiral arm even is, because the answer, the real answer, is that a spiral arm is not what you think it is at all. It's not a line of stars. It's not a solid structure. It's not a thing in the way you'd normally mean a thing. But I'm getting ahead of myself, and we have all night, and there's no need to rush toward the answer. The beauty of a puzzle like this lives in sitting with the puzzle for a while first. So let's just rest here in the strangeness of it for a moment longer. Let me lay the contradiction out one more time, slowly, the way you'd smooth out a blanket. Stars near the galaxy's center orbit quickly. Stars far out orbit slowly. This is differential rotation, and it is absolutely real, measured and confirmed, not in doubt at all. Our own sun is one of those slow outer stars, taking its 225 million years per lap, 27,000 light-years from the center. The inner stars, closer in, lap us many times while we crawl around once. So any pattern made of fixed stars, any shape drawn in actual stars across the disk, would be sheared apart by this. The fast inside would always be running away from the slow outside. A straight spoke becomes a curve, becomes a coil, becomes a smear. Within a few 100 million years, a heartbeat, galactically, the structure would be gone. And yet the structure is there, in galaxies that have been spinning for billions of years. The arms persist. The spiral holds. So either something is wrong with our understanding, or, and this is the door we're going to walk through slowly, in a little while, a spiral arm is something far stranger and far more wonderful than a line of stars. Maybe the arm isn't made of any particular stars at all. Maybe the stars are just passing through it. Maybe the arm is a pattern that the stars flow through rather than a thing the stars are stuck inside. Maybe, and I'll only whisper this for now and we'll come back to it properly, maybe the shape stays exactly because the stuff inside it never does. But that's for later. For now, just hold the puzzle. Feel how good it is. The most ordinary image in the sky, the friendly pinwheel galaxy you've seen 1,000 times, turns out to be quietly impossible. It shouldn't be able to keep its shape. The fast inside should have wound the slow outside into a blur eons ago, and it didn't. It's still there, still spiraling, still graceful, still holding. So what's holding it? That's the question we'll drift toward slowly, gently, as the night goes on. We'll find the answer, and it's a lovely one, and it has to do with traffic jams of all things, and with waves on the sea, and with the strange, beautiful idea that the most permanent things in the universe might be made entirely of motion, that something can keep its shape forever precisely because nothing in it ever stays put. But not yet. There's no hurry. Let the puzzle sit. Let the galaxy turn its slow turn. 27,000 light-years out, 225 million years per lap, The inner stars racing, the outer stars lagging, the arms that should have wound themselves into nothing still hanging there, open and bright and impossible across the whole sky, and you lying there are turning too. Right now, as you breathe, you're being carried along on that same slow carousel, part of that same impossible spiral, drifting around a distant center you'll never see, on a journey so long that all of human history hasn't completed even one full lap. You are inside the puzzle. You are made of the same patient, turning stuff. So, as your eyes grow heavier, just know that the question we're chasing isn't really about something far away out there. It's about the very thing that's carrying you right now into sleep. So breathe slowly. Let the runners blur. Let the coffee swirl. Let the arms that should be gone keep glowing anyway. We'll find out how, together, in just a little while. There's no rush at all. Let me give you one more way to feel the winding problem, because I want it planted firmly before we go looking for the answer. And because saying it again slowly is exactly the sort of thing that helps a mind drift downward into sleep. Imagine you could paint. Imagine you had a galaxy spread out before you like a vast spinning disk, and you took a brush and painted a single bright line of stars straight out from the center to the edge, a clean radial spoke like the hand of a clock pointing at 12. A simple, straight line of stars. Now let the galaxy turn. Just let it spin naturally with its differential rotation. The inside fast, the outside slow. What happens to your painted line? The inner end of it near the center races ahead, sweeping around quickly. The outer end, far out, barely creeps along. So your straight line begins to bend, the inside leads, the outside trails, and the line curves into a gentle spiral. That looks promising at first. A spiral, just what we wanted. But the galaxy keeps turning. The inside keeps racing, the outside keeps lagging, and the curve keeps tightening. The spiral wraps around once, then again and again, coiling tighter with every passing age, like thread winding onto a spool. Soon the line has wrapped around so many times that it's no longer a spiral at all. It's just a dense, blurred, smeared-out ring of stars, all the structure churned into mush. Your beautiful clean spoke is gone, wound into oblivion in just a few turns of the wheel. That is the winding problem. That is precisely, why a spiral arm made of fixed stars cannot last. It paints itself out of existence. The very rotation that should display the spiral is the thing that destroys it. And so the galaxies we see, the grand open spirals, billions of years old, arms wide and graceful and clear, they are flatly telling us that whatever their arms are made of, it cannot be a fixed line of stars. It simply cannot be. The winding would have erased it long ago. Something else is going on, something stranger and gentler and far more clever than a painted spoke. And in a little while, when you're even sleepier than you are now, we'll find out what. We'll meet the idea that solved it. We'll talk about how an arm can hold its shape for billions of years, while every single star inside it comes and goes, like cars through a traffic jam that never moves, even as the cars endlessly flow through. We'll find that the permanence of the spiral is built, impossibly and beautifully, out of pure flow. But for now, rest in the riddle. The inside spins fast, the outside spins slow. The arms should have wound themselves into a featureless blur hundreds of millions of years ago. And yet there they are, billions of years old, still open, still spiraling, still impossibly, quietly holding their shape across the dark. How? That's the soft question we carry into the next part of the night. Breathe it in and let it go, and let yourself sink a little further down. The galaxy is turning, the arms are glowing, And the answer is waiting patiently, just a little further along the path. Welcome to the Sleepy Scholar. It's lovely to have you here tonight wherever you are. Maybe you're tucked under a heavy blanket with the lamp still glowing low in the corner. Maybe you're on a train, or curled on a couch, or just lying in the quiet dark with your eyes already half closed. Wherever you are, settle in. You've found your way to the right place for tonight. And before we drift any deeper, a small and gentle thing. If you enjoy these slow journeys through the night, a quiet like and subscribe really does help this sleepy little channel keep going. Small creators like me lean on it more than you'd think. And to those of you already here, already subscribed, already part of these nights, thank you. Truly, you make this small thing possible. So tell me, before you fade away, where in the world are you watching from tonight? And what time is it in your corner of the dark? Now, here's the promise for the next while. We're going to move slowly. There's no rush at all, and there's no test waiting at the end. If you drift off before we finish, that's perfectly fine. The galaxy will still be turning when you wake, and so will these ideas, patient as ever. You don't need to grasp every detail. You don't need to follow every thread. You only need to let the words wash over you like slow water and let the wondering carry you down towards sleep. I'll try not to make it so interesting it keeps you awake. But if it does, well, at least you'll have learned something lovely, a fair trade. So, let's drift a little further into the question of the spinning galaxy, and let me give you something soft and enormous to rest your tired mind against. A sense of scale. The kind of scale that makes your own worries feel very small and very far away, in the nicest possible way. Think about where you are right now here on Earth, on this little world circling its star. And think about the sun itself, that warm, familiar thing that rises and sets, and that you almost never picture as moving anywhere. But it is moving. It is sailing through the galaxy at this very moment, carrying you and the Earth and everything you've ever known along with it in a great, slow circle around the center of the Milky Way. And how far away is that center? About 27,000 light years. Sit with that number for a moment. 27,000 years for light itself, the fastest thing there is. Just to cross the distance from the heart of the galaxy out to where we drift. We are far out in the suburbs of this great spinning city of stars, circling its bright and crowded downtown from a long, long way off. And how long does one lap take? One full circle around the galaxy? About 225 million years, some say closer to 250. We call that one trip a galactic year, a single year, but measured in the slow turning of the whole galaxy instead of the small turning of our little world around the sun. 225 million years for one loop. Let that settle. The dinosaurs that walked the Earth, the great long-necked ones, the ones that feel impossibly ancient to us, the sun has not even completed one full galactic year since some of them roamed. And since the Earth itself first formed, all those billions of years ago, the sun has carried us around the galaxy only about 20 times, just 20 laps. The whole history of our planet, every ocean and mountain and creature that ever lived, fits inside about 20 slow circles around the galactic center. Isn't that a strange and soothing thing? 20 turns. The galaxy moves so slowly, so grandly, that all of Earth's vast story is only 20 trips around the carousel. There's no hurry out here. There's never been any hurry. Everything that feels urgent to us happens in the blink between two heartbeats of the galaxy. So you can let it go for tonight, you really can. The wheel turns whether or not you worry, and it turns slowly, slowly, slowly. Now here is where I want to plant a gentle little seed of strangeness. Nothing alarming, nothing sharp, just a soft pebble of a puzzle to turn over as you sink down. Because that great slow circle, the one the sun takes 225 million years to complete, not every star takes the same time. That's the quiet detail that changes everything. The stars near the center of the galaxy, in toward that bright, crowded downtown, they complete their circles far faster than we do out here. In the suburbs, they whip around in much less time, and the stars even farther out than us, drifting in the dim outer edges, they take even longer than we do, lumbering around in their own unhurried way. The galaxy does not spin like a solid wheel. It does not turn all in one piece, the way a record turns on a turntable, the way a coin spins flat on a table, every part keeping pace with every other part. No, the inside races, the outside dawdles, every ring of the galaxy moves at its own speed, and the inner rings always outrun the outer ones. This is what astronomers call differential rotation. A long phrase, but a simple picture underneath it. Different parts rotating at different rates. The middle is fast, the edges are slow, and everything in between is a gradient, a smooth sliding scale from quick to languid as you move outward from the heart toward the rim. Now hold that gently in your mind. The fast inside, the slow outside. And let me show you the lovely little riddle it creates, because this is the puzzle the whole night turns on, and it's the kind of puzzle that's perfect for falling asleep to. Not a frightening one, not an urgent one, just a soft impossibility, sitting there, waiting. Picture the spiral arms of a galaxy, those great sweeping curves of light you've seen in photographs, winding out from the center like the trailing arms of a pinwheel, or like cream stirred slowly into coffee. Beautiful, graceful, unmistakable. Now imagine, just for a moment, that those arms were made of fixed stars, that an arm was simply a line of stars, locked in place, painted across the galaxy like a spoke painted onto a wheel. A straight, clean stripe of stars reaching from near the center out toward the edge. What would happen to that stripe once the galaxy began to turn? The inner end of it, close to the center where everything moves fast, would race ahead, sweeping around quickly. But the outer end, way out in the slow suburbs and beyond, would lag behind, plodding along at its own gentle pace. The fast inner part pulls ahead, the slow outer part trails behind, and so the stripe begins to bend, it curves, it winds. The inner end laps around again and again while the outer end is still working through its first slow circle. With every turn, the line wraps tighter and tighter around the center, coiling in on itself like a watch spring being wound down, like a rope twisted round and round a post. And here's the gentle blow of it. This winding doesn't take very long in the patient arithmetic of galaxies. Within just a few rotations, a few 100 million years, which sounds like forever, but is only a moment to a galaxy, that clean spiral stripe would be wound so tightly, smeared so thoroughly around the center, that it would dissolve, it would blur. The beautiful open spiral would close up into an indistinct, featureless disk, a smudge of stars with no arms left at all. That is the winding problem, and it is the load-bearing riddle of the whole night, so let it sink in slowly. The very rotation that should reveal the spiral is the thing that should destroy it. Differential rotation paints the arm and then, almost immediately, paints it out of existence. A few 100 million years, and it's gone, wound away into nothing. But here is the quiet contradiction that makes this so wonderful. We look out into the universe and we see spiral galaxies that are not a few 100 million years old. We see spiral galaxies that are billions of years old, ancient things, and their arms are not smudged. Their arms are not wound into a featureless blur. Their arms are open and wide, and graceful and clear, sweeping curves still spiraling outward exactly as they should not be able to, after all that turning. Billions of years of differential rotation, billions of years of the inside outrunning the outside, and still somehow the arms are there, still open, still spiraling, still holding their shape across the dark, as if the winding had simply never happened at all. And that, sleepy scholar, is the soft impossibility we rest in tonight. The math says the spiral should have erased itself an eternity ago. The sky says it didn't. Both of those things are true at once, and the only way out is that an arm cannot be what it first appears to be. It cannot be a fixed line of stars. It has to be something else, something stranger and gentler and far more clever. So what is it? That question sat unanswered for a long time. Astronomers could see the arms, they could measure the rotation, they could work out on paper that the arms should have wound themselves away centuries of millions of years ago. And yet there the arms were, patient and unhurried in the dark, curving exactly as they pleased, refusing to dissolve. The contradiction was polite in the way that only a very deep problem can be polite. It did not shout. It simply waited. And then, in 1964, two mathematicians sitting with the problem quietly cracked it open. Their names were Lin and Frank Shu. They were working on the mathematics of galactic disks, trying to understand how waves of density might propagate through a rotating sea of stars the way ripples propagate across a pond. And what they found when they worked the equations through was not what most people had been imagining at all. The arms were not solid. They were not fixed. They were not a line of particular stars that had always been there and would always be there, turning together like the spokes of a wheel. The arms, Lin and Shu proposed, were a wave. Not a wave the way we loosely use that word. A precise, physical, mathematically specific wave of density, a region of slightly higher concentration that moved through the disk of the galaxy at its own speed, on its own schedule, entirely independent of the individual stars that happened to be passing through it at any given moment. The stars were not the arm was a pattern, and the pattern was not nailed to any particular piece of matter. It was something else, something subtler and stranger, and, once you see it, almost tenderly elegant. Density wave theory, that is the name. And it is worth sitting with for a moment before we go any further, because the idea itself is so gentle and so counterintuitive that it deserves to arrive slowly, the way a good idea always does. Think about what a wave actually is. Not an ocean wave exactly, but the principle behind it. When a wave passes through water, the water itself does not travel with it. If you've ever watched a piece of driftwood on the surface of the sea, you've seen this. The wave rolls through, the wood bobs up and then down, and when the wave has passed, the wood is more or less where it started. The wave carried energy, it carried shape, it carried a moving pattern of high and low. But it did not carry the water. The water stayed roughly where it was, rising and falling as the wave moved through it, and then settling again. The arm of a spiral galaxy is something like that. Not identical. The physics of a galactic disk is not quite the physics of an ocean surface, but the same deep principle. The arm is a region where the density is slightly higher, a gentle crest in the rotating disk. And that crest moves through the disk at its own speed. The stars move through it. The gas moves through it. Matter enters the crest from one side, lingers for a while in the slightly denser, slightly gravitationally richer region, and then drifts out the other side. And the crest itself, with the arm, keeps going, keeps turning, keeps tracing its great slow curve around the center of the galaxy, not because the same stars are always in it, but because the pattern itself is self-sustaining. The arm persists while the stars flow through. Now I want to give you a second image for this because it is the one that tends to make it click. And it is an image from something much more ordinary than a galaxy, something you may have seen yourself perhaps on a long drive or a slow evening commute, stuck in traffic when you'd rather be anywhere else. Imagine a traffic jam, not a complicated one, just the ordinary kind, a long stretch of highway where, for reasons that are never quite clear from inside it, the cars have slowed, bunched up, and are crawling forward at a fraction of the speed they were doing a mile back. Cars behind the jam approach from the rear, slow as they enter it, inch forward through the thick of it, and eventually emerge on the other side and accelerate away again. The road ahead is clear. The road behind fills up with the next batch of arrivals. The jam itself sits there, roughly in the same place, for minutes or hours. It has a position, it has a shape, it persists. But here is the thing about that traffic jam. Not one single car is trapped in it permanently. Every car that is currently in the jam was somewhere else an hour ago and will be somewhere else an hour from now. The jam is not made of particular cars. It is made of a pattern of slowing, of bunching, of higher density, and that pattern can sit in roughly the same place on the highway while the cars that compose it are constantly, endlessly changing. New cars enter, old cars leave. The jam remains. A spiral arm works on exactly this principle. Stars approach the arm, approach this region of slightly elevated density, and as they do, the local gravity is just a little bit stronger than the galactic average. Nothing dramatic, not a trap, not a wall, just a gentle gravitational deepening, a subtle slowdown, the way a car eases off the accelerator when it senses the bunching ahead. The star spends a little more time in the arm than it would in the space between arms. It lingers, and while it lingers, it is part of what we see as the arm. It contributes to the slight overdensity that makes the arm real. Then, in its own time, it moves on. It exits the arm on the other side, continues on its long orbit around the galactic center, and eventually, perhaps hundreds of millions of years later, it will drift into the arm again, linger again, and drift on again. The arm stays, the star flows through. And this is why, when you hear someone describe a spiral arm as a river of stars, you can gently, sleepily know that the description, while poetic, is not quite right. A river carries its water from one place to another. The arm does not carry its stars anywhere. It simply marks a place, a moving, slowly rotating place, where, at any given moment, slightly more stars happen to be, not because they were assigned there, but because the pattern of the wave is there, and the stars are drifting through it. Lin and Shu called this a density wave, and the key word, the word that does all the work, is wave. There is one more detail that makes this picture precise, and it is worth knowing because it is concrete and real and has a name. The density wave, the pattern of the spiral arm, rotates around the center of the galaxy at what is called the pattern speed. And the pattern speed is generally different from the speed at which the stars themselves are orbiting. In the inner parts of the galaxy, the stars are moving considerably faster than the pattern. They are, in a sense, lapping it. They come around and catch up with the arm, pass through it, emerge ahead of it, and then the arm, still rotating at its own stately pace, catches up with them again eventually. In the outer parts of the galaxy, the situation reverses. The stars out there orbit slowly enough that the pattern is actually overtaking them, moving faster than they are. This difference matters because it means that if you were a star, your relationship to the arm would depend entirely on where in the galaxy you happened to live. Stars in the inner disk move through the arm from behind like faster traffic, overtaking a slow-moving lorry. Stars in the outer disk are overtaken by the arm like a slow-moving lorry being passed by the same faster car. Same highway, same jam. But from different positions, the experience is completely reversed. And somewhere between those two extremes, there is a radius, a specific ring around the galaxy's center, where the stars and the pattern happen to be moving at exactly the same speed, where neither is overtaking the other, where a star and the arm beside it are, for the duration of that particular orbit, simply moving together in step, like two people walking side by side down a long, quiet road and happening to have exactly the same pace. This ring has a name. It is called the corrotation radius. It is one of my favorite things in the whole of galactic astronomy, the corrotation radius, because it is so concrete. It is not an abstraction. It is a real place in the galaxy, a specific distance from the center, a specific circle, and it has real physical consequences. Inside the corrotation radius, stars are moving faster than the arm. They catch up with the arm from behind, enter it, slow slightly, and then move through and ahead of it. Outside the corrotation radius, the opposite, the arm is moving faster than the stars, sweeping through them like a slow wave overtaking a drifting leaf. And at the corrotation radius itself, that perfect ring, stars and arm rotate as one, locked in the same rhythm, neither gaining nor losing ground. It is, in its way, a kind of still point in the turning galaxy. Not still in any absolute sense, everything out there is moving always, but relatively still, a place where the great, slow waltz of pattern and star happens to be perfectly synchronized. The one ring where the music and the dancer are keeping exactly the same time. And this is what Lin and Shu gave us in 1964, not just an answer to the winding problem, but a whole new way of seeing what a galaxy is. Before their work, you might have thought of a spiral galaxy as a thing, a solid, rotating object, like a pinwheel or a top, with fixed structures spinning in space. After their work, it becomes something more like a weather system, a set of patterns moving through a medium. The stars are the medium, the arms are the patterns, and the patterns can persist indefinitely, not because any particular piece of matter is holding them in place, but because the mathematics of wave propagation through a rotating disk allows them to be self-sustaining. The shape is real, the shape is stable, the shape can last for billions of years, but the shape is not made of permanent members, it is made, always and only, of whoever happens to be passing through at the moment. This is the thing worth letting settle, here in the quiet of wherever you are tonight. The arm you see in a photograph of a spiral galaxy, that luminous, sweeping curve, is in some sense one of the oldest structures in that galaxy. It has been turning there, roughly where it is, for an enormous span of time. And in another sense, it is brand new. The stars in it right now were somewhere else an hour ago. Galactic hours, astronomical hours, millions of years ago, and they will be somewhere else again. The arm is ancient and always changing simultaneously, permanent and made entirely of motion at the same time. There is something calming about that, I think, if you let yourself feel it instead of just know it. The most durable things are not always the most rigid. Sometimes the most enduring shape is the one that holds its form by letting everything inside it flow freely through. A standing wave on the surface of a stream where the water pours over a rock. The wave stays, the water is never the same water twice. A flame where the shape is constant and the molecules of burning gas are consumed and replaced thousands of times a second. The arm of a spiral galaxy where the pattern endures for billions of years while the stars that make it visible are in constant, endless, unhurried procession. The permanence is made of flow. Now, we have the answer to the winding problem. The arm doesn't wind up because the arm is not a fixed line of stars. It is a wave, and the wave propagates at its own pattern speed, slow and steady, while the stars drift through it. Differential rotation is no longer a threat to the arm's existence. It is, in a sense, the very thing that makes the arm possible. The difference in speeds between the pattern and the stars is what creates the flow-through, what keeps the arm perpetually refreshed with new material, what allows the traffic jam to sustain itself in the same place on the highway year after year. But we are not quite done yet, because there is something else. Something that I think is even more beautiful than the wave itself. Hiding inside the question of why the arms are so bright. Because they are extraordinarily bright, you have probably seen photographs of spiral galaxies, M51, the Whirlpool Galaxy perhaps, or the Andromeda Galaxy, or any of the thousands of spirals that populate the pages of astronomy books and the walls of science museums. And the arms in those photographs are luminous things. They glow. They are not subtle. They are unmistakable, sweeping curves of brilliant light, almost painfully bright in comparison to the darker spaces between them. And you might reasonably assume, given everything we've been discussing, that this brightness reflects density, that the arms are bright because there is so much more matter in them, so many more stars packed so much more tightly than the space between, that the arm is essentially a crowded place, and its crowdedness is what makes it shine. But here is where the picture gets a little stranger and a little more wonderful. The density contrast of a spiral arm, is the amount by which the mass in the arm exceeds the average mass of the disk around it, is actually quite modest. The arm is not dramatically heavier than the space between arms. On average, the arm holds something like 10 to 20% more mass than the surrounding disk. Not 10 times more, not even twice as much, just 10 to 20%. 10 to 20% more mass. And yet in photographs, the arms can look 100 times brighter than the interarm regions. How? The answer is star formation, and it is one of the most beautifully self-contained mechanisms in all of astrophysics, because it explains not only why the arms glow, but why they glow the particular colors they do. When gas, great clouds of cold hydrogen and helium and dust that drift slowly through the galactic disk, when this gas approaches the density wave, something happens to it. The gas is compressible in a way that stars are not. Stars, being massive, dense objects on long orbits, feel the gentle gravitational pull of the arm and slow slightly, lingering a little longer in the arm region, and then move on without being fundamentally changed. But the gas is different. The gas is diffuse and cold, and when it encounters the slight overdensity of the arm, when it drifts into that gentle gravitational slope, it gets compressed. Imagine drifting fog on a country road, and the road narrows slightly ahead, and the fog thickens as it's squeezed into the narrower passage. Something like that. The gas piles up a little at the leading edge of the arm. The density of the gas rises. And in the cold, dark corners of the universe, when gas gets dense enough, something wakes up inside it. Gravity, not the smooth, large-scale gravity of the whole galaxy, but the local gravity between the molecules in the gas cloud itself. When the cloud gets dense enough, its own self-gravity starts to win against the thermal pressure pushing the cloud outward. The cloud begins to collapse inward, slowly at first, then faster. It fragments into smaller clumps. Each clump collapses further. The temperature rises as the material falls inward and pressure builds. And eventually, in the hot, dense heart of a collapsing fragment, the temperature climbs high enough that hydrogen nuclei are moving fast enough and close enough together that they fuse. A star ignites. This is happening right now in the spiral arms of galaxies across the observable universe. The arms are not just patterns of density. They are the galaxy's nurseries. They are where stars are born, triggered by the compression of gas as it drifts into the density wave. The arm doesn't create the gas was already there, drifting in the disk. But the arm provides the compression event, the gentle squeeze that tips a cold, quiet cloud from merely existing into actively collapsing. The arm is the midwife. And now the brightness makes sense. Because among the stars being born in these compressed gas clouds are some extraordinarily luminous ones. When a cloud collapses and fragments, it produces stars of many different masses. Most of the stars born are small and dim. They will live for billions of years and never be particularly bright. But scattered among them, in every burst of star formation, are a few exceptional ones. Massive stars. Stars many times heavier than our Sun, some of them tens or even 100 times more massive. These are classified as O-type and B-type stars by spectral type, and they are extraordinary objects. They are blue. A vivid, almost electric blue because they burn so hot that the peak of their radiation is at the blue and ultraviolet end of the spectrum, and they are brilliant. Not bright the way a candle is bright. Brilliant the way a searchlight aimed at your window from a mile away is bright. A single massive O-type star can outshine our Sun by hundreds of thousands of times. In a galaxy, a small cluster of these blue giants can light up an entire arm. But here is the piece that locks the picture together. These stars burn fast, enormously fast, relative to the universe's timescales. A star like our Sun is estimated to live for about 10 billion years. A massive O-type star lives for a few million years. It burns through its fuel in an eye blink of cosmic time, and then it dies, often spectacularly, in a supernova. A few million years, and the arm, the density wave, is moving at its pattern speed, and the stars, once born, begin orbiting on their own paths. In a few million years, a newly born star does not travel very far from the place where it was born. It does not have time to drift far from the arm before its short, brilliant life is over. And so the massive blue stars are always found close to where they were born, which means they are always found close to the arm, which means the arm, viewed from a distance, is ringed with these brilliant blue stars, not because the arm is especially massive, not because it contains so much more matter than the space around it, but because it is continuously, actively creating some of the most luminous objects in the galaxy. And those objects, being short-lived, never wander far before they're gone. The arm glows blue because it is a factory of blue stars. The factory never stops running. The gas drifts in, the wave compresses it, the compression collapses it. The collapse ignites the stars burn brilliant blue for a few million years, and then they're gone. But by then, more gas has drifted in, more stars have ignited, and the blue light at the arm's edge is replenished. The arm maintains its glow not by holding on to anything, but by constantly making new light from new stars. And alongside the brilliant blue stars, there is something else marking the arm. The same compressed gas that is collapsing into stars is also, in the places where it hasn't quite collapsed yet, being lit up from the outside by the radiation of the newborn stars inside it. Hydrogen gas, when bathed in intense ultraviolet light from a hot young star, begins to glow. The ultraviolet radiation strips electrons from the hydrogen atoms, and when the electrons fall back in, they release energy as visible light, a particular, unmistakable shade of red and pink. These glowing hydrogen clouds are called HEI regions. The H is hydrogen. The Ti means singly ionized, meaning an electron has been removed. And they are the soft pink patches you see in deep photographs of spiral galaxies, clustered along the arms like lanterns hung along a winding road. Chi regions, the pink glow of gas that has been kissed into fluorescence by the ultraviolet breath of very young stars. They are not ancient, they are almost impossibly fresh. They are light from the moment of creation, still happening. And at the very edge of the arm, on the inner side, the side from which the gas is approaching as the density wave sweeps through the disk, there is something darker, a lane of dust. The compressed gas and dust at the wave's compression front, before it has had time to collapse and ignite into stars, appears as a dark stripe against the brighter material behind it, a dust lane. If you look at a detailed photograph of a grand design spiral galaxy, you can often see these dark lanes tracing the inner edges of the bright arms like a shadow preceding the light. The sequence, moving across the arm from one side to the other, tells the whole story. On the leading edge, the compression front, a dust lane, dark and dense, where the gas has been squeezed but not yet lit. Then the pink of HIE regions, gas beginning to be ionized by the very first newborn stars. Then the brilliant blue of the young massive stars themselves, newly ignited and shining at full intensity. And behind them, as you move toward the arm's trailing edge, the colors shade slightly redder, slightly older. Stars that were born in a slightly earlier wave of compression are a few million years further along in their lives and have drifted just a little further from the birthplace. A gradient of time visible in color. The arm is not just a place in space, it is a sequence in time laid out across its own width, younger on one side, older on the other, the whole slow story of gas arriving, compressing, igniting, and aging, written in light across a curve of star field. And all of it, the blue stars and the pink nebulae and the dark dust lanes and the shifting colors, all of it is riding on a gentle ripple of density that is, in terms of mass, only about 10 to 20% above average. The arm is mostly light. It is almost entirely light. The substance underneath it, the extra gravity that triggers the compression that makes the stars that make the glow, is barely there by the standards of the mass budget, a whisper of density amplified into a blazing curve of color by the alchemy of star formation. The spiral you see in a photograph is not where the mass is concentrated. It is where the mass is currently giving birth. There is something in that which I find quietly profound. The places in the universe that shine brightest are not always the places that have the most. Sometimes they shine because of what they are doing, because of the process, the event, the moment of transformation, rather than because of what they contain. The arm is bright not because it is rich, but because it is alive, active, continuously making something new from what drifts through it. And somewhere in all of that, somewhere in the density wave and the traffic jam of stars and the blazing blue newborns and the pink clouds of glowing hydrogen, is the answer to the question the title asked. How does a spiral galaxy keep its shape? Not by holding anything fixed, not by resistance or rigidity or permanence of material. It keeps its shape by being a wave, by being a pattern that regenerates itself, that sustains itself through the very flow of material through it, that lights itself up from the inside with the constantly renewed fire of star formation. The shape endures because nothing in it is required to stay. That is the answer. And it is, I think, one of the stranger and more beautiful answers that physics has ever produced. The persistence of form through the freedom of content. The arm stays open and graceful across billions of years because it is not attached to anything. Hold that thought if you are still awake enough to hold thoughts, because we are not finished. There is more to the picture, complications and nuances and a fuller honesty about what the universe actually does, which is always a bit more complicated than any single elegant theory suggests. But for now, rest in this. The spiral arm is a traffic jam made of starlight. The stars are only the cars passing through. And the jam has been sitting in roughly the same place for longer than the Earth has existed. Let that be enough for a moment. Let the idea breathe. Somewhere out there in the dark, right now, a cloud of hydrogen gas that has been drifting quietly through the disk of a galaxy for millions of years is just now reaching the edge of a density wave. It is just now beginning to feel the gentle squeeze of the compression front. In a few million years, a blink, cosmically, it will ignite. It will burn blue and brilliant for a short while. It will light up the arm, and then it will be gone. And other gas will have arrived, and the arm will be just as bright as it ever was, because the process never stops. The galaxy keeps its shape the way a flame keeps its shape, by burning, always new. And here is the thing that surprises almost everyone who first hears it. You would be forgiven for imagining that a spiral arm to be so visible, to be so bright against the dark disk of a galaxy, must be a dense and heavy thing, a thick river of stars, a great concentration of matter wound into that graceful curve. When you look at a photograph of a grand design spiral, and if you have ever seen one of those photographs, you know exactly what I mean, that almost unbearable beauty of two curving arms sweeping outward from a glowing core. It looks substantial. It looks like something you could measure and weigh and point to and say, there, that is where most of the galaxy lives. But it isn't. The density contrast of a spiral arm over the surrounding disk, the amount of extra matter packed into the arm compared to the quieter space on either side, is on average only about 10 to 20%. That is all. If you could somehow weigh a column of space running through the bright heart of a spiral arm and compare it to a column of the same size running through the dimmer region just beside it, the arm would be heavier by roughly 1 part in 10. A gentle ripple, a soft pressure, not a wall, not a river, not a ridge of concentrated mass, just a modest, quiet compression in the flow of stars and gas, moving slowly through the disk like a long, low swell on a very calm sea. And yet the arm blazes. So if the mass isn't what's making it bright, what is? The answer is light. The answer is birth. The answer is, in a way, the most vivid possible illustration of what a density wave actually does. And it is worth slowing all the way down here, because this is one of those moments where the physics becomes something you can almost feel. When a cloud of gas drifts through the dark disk of a galaxy, it is in no particular hurry. It has been drifting for millions of years, perhaps tens of millions, moving along its slow orbit, cold and dark and patient. It is mostly hydrogen, a giant, diffuse, invisible thing, not a cloud you would recognize as a cloud, nothing like the rounded shapes of a summer sky, but a vast and wispy accumulation of molecules spread across dozens of light years, so thin that in most places it would count as a better vacuum than anything we can produce in a laboratory on Earth. And yet it is there, and it is moving, and eventually, as everything in the disk eventually does, it reaches the edge of a spiral arm. And then something changes. The gas begins to feel a pull. Not a sudden dramatic yank, nothing violent. This is a gentle universe, slow and patient. But the slightly higher density of the wave region means slightly more gravity. A gentle compression begins, the cloud drifts in, the molecules crowd a little closer together. The temperature begins to tick upward in some places, and in other places the density climbs just enough that a new force starts to assert itself. The cloud's own self-gravity, which had been too weak to matter when the gas was spread thin, starts to pull its own parts inward. This is the trigger, this is the cascade. Once a cloud of gas becomes dense enough that its own gravity can overcome the pressure pushing outward, it collapses. And it does not collapse gently or gradually. It collapses fast, in astronomical terms, catastrophically fast, over a mere million years or so, and as it falls inward, it heats. And at the center of that collapse, when the temperature and pressure climb high enough, hydrogen nuclei begin to fuse. A star ignites. More precisely, many stars ignite. Gas clouds don't produce one star, they produce whole nurseries of them, clusters of newborns in a vast creche of warm, ionized hydrogen, lighting up the cloud from within. And among those newborns, there are always some that are extraordinary, massive, hot, ferociously luminous. These are the O-type and B-type stars, the blue giants, the stellar aristocracy of mass and brightness. An O-type star can be tens of times more massive than our Sun, and it burns with a temperature so high and a luminosity so extreme that it outshines the Sun by tens of thousands of times. Stand next to one and you would be vaporized before you could form a thought about it. But here is the crucial detail. Here is the thing that explains the brightness of the spiral arm without requiring the arm to be heavy. These blue giants burn fast, catastrophically fast by the standards of stars. A star like our Sun can burn steadily for about 10 billion years. We are currently roughly halfway through that life. But an O-type star, with all its mass and all its furnace heat, exhausts its hydrogen in only a few million years. Some last only 1 or 2 million years. Massive B-type stars are similarly short-lived by stellar standards, a few tens of millions of years at most for the less extreme ones, far less for the most extreme, a few million years. Set beside a spiral arm that has persisted for billions, set beside a galaxy that has been rotating for longer than that, these stars do not have time to go anywhere. They are born inside the density wave, inside the arm, because that is where the compression triggered their formation. And they die inside the arm, or very close to it, because they exhaust themselves before they can drift out the other side. They blaze and they burn, and they pour light outward in every direction for their brief lives, and then they are gone, exploding as supernovae or collapsing in on themselves, and meanwhile, the arm around them is already receiving the next generation of gas clouds, already compressing them, already lighting new fires. The arm is not a concentration of matter, it is a production line of light. And those new blue stars, those short-lived brilliances, they are so disproportionately bright that they utterly dominate the visual appearance of the arm. Older stars, and stars like our Sun, which may have passed through the arm long ago and emerged on the other side and continued their quiet orbits. Those stars contribute their light too, but they are dimmer individually, and they are spread all through the disk, not concentrated into the arm. It is the newborns that paint the arm blue. It is the newborns that make it visible against the dark. This is a thought worth sitting with if you are still with me. The most brilliant, most visually striking feature of a spiral galaxy, those glowing arms you see in photographs, the thing that makes the galaxy look the way it does, is made almost entirely of the youngest, most short-lived stars. The arms glow not because they are old and enduring, but because they are constantly and urgently new. The brightness is not a record of history, it is a flag planted on the present moment. It says, here, right now, stars are being born. And not only stars. Alongside those brilliant blue newborns, the surrounding gas is lit up in a different way. The fierce ultraviolet radiation pouring from the hot young O and B-type stars is intense enough to strip electrons from the hydrogen atoms nearby, ionizing them, turning cold, neutral hydrogen into a glowing plasma of charged particles. When those electrons eventually recombine with their protons, they release light, and the particular wavelength most characteristic of that recombination glows a deep, warm pink. These are the HII regions, regions of ionized hydrogen, and they are the pink and red patches you see studded through spiral arms in true color photographs. They are like neon signs hanging outside a star factory. They mark precisely the places where the compression has done its work and new suns are flickering into existence. So the arm has a particular kind of signature, a fingerprint that tells you exactly what it is doing. The blue from the short-lived massive stars, the pink from the HIE regions glowing in the newborn's radiation, and, threading through it all, marking the very edge where the compression is freshest and most forceful. The dust lanes. A dust lane is a dark stripe. In photographs of spiral galaxies seen at certain angles, you can sometimes make them out, thin dark ribbons running along the inner edge of a bright arm, like a shadow sewn into the light. They form because the interstellar dust, tiny grains of carbon and silicate, smaller than the particles in cigarette smoke scattered through the disk, gets concentrated along with the gas when the compression front arrives. Dust absorbs light. Where it piles up, it blocks the view behind it, creating those characteristic dark streaks, and the dust lane sits on the leading edge of the arm, on the side where the gas is just arriving, where the compression is just beginning. That is where the density is rising fastest. That is where the clouds are being squeezed hardest. And just past the dust lane on the inside of the arm, you find the HII regions blazing, and then the young blue stars still close to their birthplace. This sequence, dust lane, then pink HI regions, then blue young stars, is not random. It is the signature of a density wave doing its work, written across the face of a galaxy in different kinds of light. And there is a softer gradient too, a color story that plays out across the full width of the arm if you know how to read it. The stars entering the arm on the leading side, just past the dust lane, they are the freshest. They are the newest born, still blue, still hot, still pouring out ultraviolet light with the urgency of youth. But as you scan across the arm toward the trailing edge, the stars you find there are a little older. They were born when that part of the gas cloud passed through the compression, a little earlier in the orbital sequence. They have had a few more million years to cool and age. Their blue has faded a little toward white, toward yellow. The arm's color shifts across its own width, from blue-white on the leading side to slightly warmer tones on the trailing side. A slow gradient from birth to early childhood, written in wavelengths that our eyes can sometimes, with the right equipment and the right kind of attention, just barely read. It is a subtle thing, a nuanced thing, and astronomers are careful to note that the details of this color gradient depend on the geometry of the galaxy, on which direction the arms are trailing, on the exact orientation toward us. It is not a clean universal rule, but the principle is real, and the mechanism behind it is the same one we have been tracing all along. Gas enters, compresses, ignites. Stars are born and age as they move through and out the other side of the wave. The arm is a river of time as much as a river of space. Think, for a moment, about what that means for our own position in all of this. Our Sun, and we have established already that it sits about 27,000 light-years from the Milky Way's center, taking somewhere between 225 and 250 million years to complete a single orbit. Our Sun lives not in one of the great spiral arms, but between them. We are in a smaller structure called the Orion Arm, sometimes called the Orion Spur, a minor arm or branch tucked between the larger Sagittarius arm inward and the Perseus arm outward, with the Scutum Centaurus arms sweeping beyond. We are, in a sense, in the quieter water between the waves, not in the production line but watching it from a comfortable distance. And because we sit in this in-between place, the Sun has, in its roughly 4.6 billion year life, passed through actual major spiral arms multiple times, at the slow, majestic pace of galactic dynamics. Each time it drifted into one of those arms, the gas around it would have been compressed, star formation in the neighborhood would have increased, and the sky of that ancient Earth, if there had been eyes to see it, would have been lit by more new, brilliant blue stars than it is today. Some researchers have wondered whether these passages through the denser, more active arm regions might be connected to periods of increased cosmic ray flux or subtle changes in the solar neighborhood's environment over geological timescales. The ideas are intriguing and still debated, but the point is simply this: the spiral arm is not a backdrop. It is a place you pass through. It changes the neighborhood. It is an event. And there is something else worth knowing about the arm we do see around us, the nearby structure of the Orion spur itself. We see it because of those same short-lived blue stars, the young O and B-type stars in our region of the galaxy, the ones that were born in recent millions of years and haven't had time to travel far. They mark where we are. They mark that we are in a structure, even if a modest one. The Orion Nebula itself, that great glowing cloud you can sometimes see with the naked eye as a slightly fuzzy patch in the sword of Orion, is one of those HIE regions, a nursery actively producing new stars right now, not that far from us in galactic terms. It is a small local example of the same process happening all through the arms of every spiral galaxy we can observe. Star formation happening now, birth constant and ongoing. This is one of the quiet revelations of looking at the night sky with an understanding of what the light is telling you. Those bright stars in the familiar constellations, many of them are the young ones, the hot ones, the recent arrivals. The sky you look at is not a museum of ancient lights arranged for your contemplation. Parts of it are fresh, parts of it are new, parts of it are the current edge of the wave. Now, we have been spending time in this one beautiful corner of the mechanism, the brightness, the births, the blue stars, and their brief brilliance. But there is one more thread to pull before we move on, and it connects back to something said earlier. The corrotation radius. We touched on it as a kind of boundary, the one special ring where stars and pattern move at the same speed, where a star sits right alongside the arm it is orbiting through and neither overtakes the other, nor falls behind. And now that we have thought about star formation in the arms, there is something more to say about that special place. Inside the corrotation radius, in the inner regions of the disk, the stars are moving faster than the pattern speed of the arm. They overtake the arm, they drift through it from behind and exit ahead. This is the traffic jam picture in its clearest form. The stars are the fast cars, and the jam is the slower disturbance they catch up to, slow through, and pass. The gas gets compressed, the stars are born, the arm glows, all in the inner disk, all in this regime where the stars are the faster moving thing. Outside the corrotation radius, the situation reverses. The arm, the pattern, moves faster than the stars. The arm is the faster thing, overtaking the stars. Gas still gets compressed as the arm passes through, still forms stars, still lights the arm, but the geometry of the encounter is mirrored. Which side of the arm the gas enters from, which side the young stars end up on, which edge bears the dust lane, all of this can be different on the far side of the corrotation circle. The arm is the same kind of structure, but the choreography of what moves relative to what is flipped. And right at the corrotation radius itself, there is a particular stillness. Stars there keep pace with the arm. They sit in it, drift with it, are not swept through in either direction. It is, in a strange way, the one place where the traffic jam analogy breaks down a little, because here a car is perfectly matched to the speed of the jam, and it stays. Not forever. Small perturbations, the slight nudges of gravity from neighboring stars, will eventually nudge it out. But for a while, at the corrotation radius, the galaxy's two rhythms, the rhythm of the matter and the rhythm of the wave, are synchronized. It is the one quiet place in a disk full of motion. The exact position of this radius in the Milky Way is something astronomers are still working to pin down precisely. The measurements are genuinely difficult, We are inside the galaxy, trying to take its measure from a single point within it, like trying to draw a map of a forest from somewhere in the middle of it. Different methods give somewhat different answers. The best estimates for our galaxy's corrotation radius vary between studies, and the pattern speed of the Milky Way's spiral arms, the rate at which the wave itself rotates, is still an active area of research. Science, as always, is more honest about what it doesn't know than a tidy classroom explanation would lead you to believe. And there is one more nuance to the picture of star formation that is worth a quiet moment of your attention. Not all the stars being formed in the arms are those spectacular, short-lived blue giants. Alongside the O-type and B-type stars, the same gas clouds that collapse in the compression zones produce stars of every size. Small, cool, dim red dwarfs that will burn for tens of billions of years, medium-weight stars like our Sun, and yes, the massive blazing ones that will die in a few million. The arm produces all of them, but it is only the massive ones that die before they can leave, and it is only those that dominate the arm's visible light. The smaller stars born in the same nurseries at the same time simply drift on. They carry on orbiting long after the blue giants they were born alongside have exploded and gone. They pass out through the arm's far edge and continue into the quieter disk. They become the population of ordinary stars spread through the galaxy. And in time, some of them pass through arms again, and the cycle repeats. Our Sun, almost certainly, was born in a denser region, possibly in or near a spiral arm, roughly 4.6 billion years ago. The gas cloud that collapsed to form it has long since dispersed. The blue giant siblings it may have had are gone and forgotten, and the Sun has been quietly orbiting, passing in and out of arm regions ever since. It carries no record of where it was born. It has moved on, as the stars always do, as the whole disk always does. The arm that marked its birth, if there was one, is still there. Or rather, the pattern is still there. The density wave is still propagating, still compressing new gas, still lighting new fires. Different gas, different stars, same arm. The flame keeps its shape by burning. And so the arm glows, not because it is heavy, not because it holds the galaxy's mass, but because it holds the galaxy's births. The 10 to 20% extra mass provides the compression. The compression provides the trigger provides the newborns, and the newborns, blazing blue and brief, provide almost all the light that makes those arms so heartbreakingly beautiful in photographs. There is something almost paradoxical about it when you turn it over slowly. The most permanent-looking feature of a spiral galaxy, the thing that gives it its name, its shape, its identity, is built from the most temporary inhabitants. The massive blue stars that paint the arm bright are the shortest-lived stars in the galaxy. They are the mayflies of the stellar world, burning hard and fast and gone within a few million years. And yet it is precisely their short lives that make the arm visible, precisely their refusal to last that keeps the arm's light fresh and new. If they lived longer, they would drift out of the arm before they died, and the light would spread and diffuse through the disk. And the arm would lose its sharpness, its definition, its beauty. The arm is bright because its brightest stars don't survive long enough to leave it. Think about that for a moment. Let it settle the way a thought settles when you are not quite asleep but not quite fully awake either. The permanence of the structure depends on the impermanence of its brightest elements. The arm endures because those stars burn out. If they lasted forever, the arm would dissolve into a blur. It is permanence made of impermanence all the way down. The traffic jam stays in place because individual cars or individual stars move through it. The arm keeps its shape because individual clouds of gas are swept up, burned briefly bright, and released. And the light that makes the arm visible is provided by stars that die inside it before they can escape. Every level of the picture reinforces the same quiet theme: form without fixedness. A pattern that persists not because anything holds it together, but because the process that generates it never stops. Outside, somewhere in the dark that you cannot see, even on the clearest night, even with the largest telescope, there are galaxies in which this is happening right now. Gas clouds arriving at a density wave, the slow gathering of pressure, the invisible cascade toward collapse, the ignition. Blue light spreading outward across a galaxy that from our distance looks like a fixed and finished thing, a painting hung in space, unchanged. But it is not unchanged. It has never been unchanged. In the time it takes light from that galaxy to reach us, millions or billions of years, depending on how far, those blue stars we are seeing have already died and new ones have been born, and the arm has been relit 1,000 times over. We see a photograph of a moment. The galaxy itself is a process, continuous and patient, the same wave pattern moving through ever new material, ever since the disk formed and the first instabilities in the gas began to organize themselves into those graceful curves. If you are still listening, still here in the quiet, if the lamp is still on, or if you are somewhere between waking and not, let this be the last thought of this part of our journey. The arms of a spiral galaxy are not walls and they are not rivers. They are not concentrations of stars and they are not fixed structures pinned to the disk. They are regions where the density is slightly higher, just slightly, by that modest 10 to 20%, and where that slight increase in density is enough to compress the wandering gas and trigger the formation of new suns. The light that makes them beautiful comes from those new suns, from the briefest and most brilliant of all the stellar generations, born inside the wave and gone before they can leave it. The dust lanes mark where the compression is freshest. The HII regions glow pink where the new stars are already ionizing the gas around them. The young blue stars blaze along the arm's brightest ridge, and all of it, the dust, the glow, the blue fire, is moving. Everything is moving. The gas drifts in, the stars are born, the stars drift on or die in place, and new gas arrives to take their role. The spiral arm is not a structure at all, it is an event, a long, slow, endlessly repeating event, a production of light and stars that has been running for billions of years without intermission, without pause, without needing anything to be fixed or permanent or held in place. The shape is held not by what stays, but by what keeps moving through. And that, in its quiet way, is one of the more extraordinary things the universe does. It makes enduring beauty out of constant change. It keeps a shape, not with walls, but with a process. It writes a pattern in the sky that lasts longer than the solar system has existed, and it writes it entirely in things that never stop moving. And now let us look more closely at the arm itself, at what it is actually made of in this moment, at this scale, because here is something that tends to surprise people when they first encounter it. The spiral arm, that dramatic sweeping curve of light that dominates photographs of galaxies like M51 that makes a spiral galaxy one of the most immediately beautiful objects in the known universe, is not particularly heavy, not compared to what surrounds it. The density contrast between the arm and the quieter disk on either side is, in most cases, only around 10 to 20%. 10 to 20% more mass per unit volume. That is a surprisingly modest difference for something that looks so dramatic. Imagine a crowd gathered in a doorway. The people flow through the building steadily, but near the door there are just a few more of them per square meter than in the corridors on either side. The doorway does not contain most of the people. It does not trap them. It simply sees a slightly higher density at any given moment, And that slightly higher density is enough to give the doorway a visible presence, a shape you can point to, something recognizable and persistent, built from a fraction more people than the space around it. The spiral arm is something like that doorway, barely heavier, barely denser, and yet unmistakable from 100 million light-years away. So if the arm is not particularly massive, why does it blaze so brightly? The answer is the stars that are born inside it. Specifically the youngest and most luminous stars that the universe knows how to make. When a cloud of gas drifts into the density wave, drifts into the slightly compressed region where the arm is passing through, the extra pressure that the wave provides is enough to tip the cloud over the edge. Gravity takes hold. The cloud collapses. New stars ignite. And among those new stars, in the brightest and most extravagant end of the population, are what astronomers call O-type and B-type stars. Massive stars, furiously hot stars, stars that burn with a blue-white intensity that makes our own sun look warm and modest by comparison. These O-type and B-type stars are extraordinary things. They can be tens or even hundreds of times more massive than the sun. They shine with a luminosity so extreme that they outshine their neighbors by factors that are difficult to picture. A single one of these blue giants, if placed at the sun's position in the sky, would turn the sky a pale blue even in daylight. They are almost absurdly bright. But they do not last long. That is the crucial point. That is the thing that makes the arm glow the way it does. These massive blue stars burn through their fuel at a staggering rate, and as a consequence they live for only a few million years. A few million years is nothing on the timescales we have been drifting through tonight. The Sun is 4.5 billion years old. The Milky Way is something like 13 billion years old. A few million years is a heartbeat, a blink, a brief, bright flash in the long, slow darkness of galactic time. And because the stars live for only that brief time, they do not have a chance to travel far. They are born inside the density wave, and they are gone, collapsed, exploded, faded, before they can drift any significant distance from the arm that made them. They are newborns who never leave the room where they were born. And so the arm is always full of them, not because they accumulate over time, but because the arm is constantly producing new ones to replace the ones that die. The arm is a factory, running continuously, always lit from within by the most recent batch of brilliant young stars. The blue light that traces the spiral in every photograph is the light of stars that were born recently. Recently on the galactic scale, meaning within the last few million years. And it is the light of stars that will be dead or dying long before the arm itself has changed its shape. The arm glows because it is always young inside, even though the arm itself is ancient. And alongside that blue fire, you will find the other markers of this constant birth. The dust lanes, which appear as dark ribbons on the inner edge of the arm, where the compression of the density wave is freshest and the gas is being pushed together most forcefully before it collapses. These dust lanes mark the front of the wave, the place where the process begins, where the gas first feels the squeeze. Then, just beyond, the HII regions, clouds of hydrogen gas that have been ionized by the ultraviolet radiation pouring from those new blue stars, lit up from within, glowing in that characteristic soft pink that you see in images of star-forming nebulae. The Orion Nebula, which you can see with the naked eye on a clear night, is a small and nearby example of exactly this kind of region, a cloud of gas, freshly compressed, newly lit by the young stars it has just produced. And if you could stand outside the galaxy and look at a single arm from above, and if you had instruments sensitive enough to measure the colors with precision, you would see something like a gradient written across the arm's width. On the leading edge, the side where fresh gas is arriving and the compression is newest, The stars are bluer, younger, hotter. They are the most recently born. Then as you move across the arm toward the trailing edge, the stars grow slightly older, slightly redder, slightly further along in their lives. They entered the arm, they were born, or they passed through, and now they are beginning to drift away on the far side, carrying with them the slightly aged color of stars who have been burning for a few million years longer than their counterparts on the other side. The dust lane marks the front. The blue ridge marks the nursery. The reddening trail marks the exit. The arm is not just a shape, it is a sequence, a story written in color across a width of a few thousand light years, readable if you know what you are looking at. Gas arrives, compresses, collapses, ignites blue, glows pink, ages, departs. Then more gas arrives. And now, having rested there for a moment in the quiet color gradient of a spiral arm, the blue on the leading edge, the pink HE regions blazing, the dust lane marking where compression bites hardest, it is time to step back even further. To look not just at one arm or one star or one crossing, but at the whole population of spiral galaxies in the sky. Because not all of them keep their shape in quite the same way. And that turns out to tell us something important about how much of what we have described is universal, and how much depends on the particular life and circumstances of a given galaxy. Of all the spiral galaxies we can see, there are hundreds of billions of galaxies in the observable universe, many of them spirals. Only about 10% are what astronomers call grand design spirals. 10%. That seems surprisingly small, doesn't it? A grand design spiral is what you probably picture when someone says the words spiral galaxy. Two long, clean, sweeping arms, roughly symmetric, curving outward from the nucleus in a graceful, coherent, almost impossibly elegant shape. They look like pinwheels. They look like the galaxies on the covers of popular science books. They look, in a word, designed. The textbook example, the one that appears in almost every introductory astronomy course, the one that has probably been printed on more posters than any other galaxy outside our own, is M51. You may know it by another name, the Whirlpool Galaxy. It sits about 23 million light-years away in the constellation Canes Venatici, and through even a modest telescope it is breathtaking. Two arms, clear, symmetric, reaching outward in long, smooth curves from a bright central core. If you have ever seen a photograph of a galaxy and thought, yes, that's exactly what a galaxy looks like, there is a reasonable chance you were looking at M51. And M51 is, in this context, something of a gift because it makes the mechanism visible, because M51 is not alone. Hovering close beside it, connected by a faint bridge of stars and gas, is a smaller companion galaxy called NGC 5195, and that small companion is not decorative, it is functional. It is, in a meaningful sense, partly responsible for the beauty of the larger galaxy's arms. Here is how that works. When two galaxies pass close to one another, this happens in the slow, patient timescale of the cosmos, their gravitational fields interact. The smaller galaxy's gravity pulls on the disk of the larger one. It tugs. And that tug, applied steadily across the disk, can excite and reinforce the density wave pattern. It can organize what might otherwise be a patchy, fragmented structure into something cleaner and more coherent. The companion essentially reaches out and combs the spiral into shape. Not all at once, not consciously, not deliberately, but through the patient and inevitable mathematics of gravity acting over hundreds of millions of years. So M51's arms are partly a gift from NGC 5195. The smaller galaxy's tidal pull has helped sculpt the pattern into its extraordinary clarity. And this is not unique to M51. Many grand design spirals, when you look carefully, turn out to have a companion nearby or to have had one in the recent past. The tidally driven density wave is one of the cleaner ways to get two long, symmetric, stable-looking arms in a disk galaxy. But what about the other 90%? What about all the spiral galaxies that do not look like that? That do not have two clean, sweeping arms, but instead something more like a patchwork? A woolly, fragmentary collection of shorter arm segments, clumps, spurs, short curved arcs, the suggestion of a pattern without the pattern itself being fully there. These are called flocculent spirals. The word comes from the Latin for tuft or wisp, the same root as flocculent in chemistry, where it describes a precipitate that forms in soft, irregular clumps rather than clean crystals. And it is a good word. A flocculent galaxy looks, under the right conditions, a little like carded wool or clouds, or the surface of a river, where many small eddies have formed without organizing into a single current. In flocculent spirals, the grand standing wave picture that Lin and Shu described in 1964 is not the whole story, or it may not be operating at all. What seems to be happening instead, or in addition, is something that astronomers describe as self-propagating star formation, combined with the shearing effect of differential rotation. A region of gas becomes unstable and collapses into stars. Those stars, the hot, massive young ones, pour out ultraviolet radiation and eventually explode as supernovae. The shock waves from those explosions compress nearby gas. That nearby gas collapses into more stars. The process propagates the way a spark can travel across dry grass, not because something organized it from outside, but because the conditions in one place trigger conditions in the next place. And as all of this happens, differential rotation, the same differential rotation that would wind up a fixed arm, the same winding problem we described much earlier, takes each little cluster, an arc, and stretches it, shears it sideways, curving it into a short arc before it dissipates. You get many short, curved, arm-like features, all being constantly created and destroyed and recreated, but never quite organizing into the two long, clean arms of a grand design spiral. Computer simulations of galaxy disks have shown this process very beautifully. When you model a disk with the right conditions, a realistic density, a realistic temperature, realistic gravitational physics, and you let it run for billions of simulated years, you see arms appear, shear, dissolve, and reform. Transient, recurrent, never quite the same twice, but always producing something that looks, from a distance, like a spiral pattern. This is what astronomers sometimes call the transient and recurrent picture of spiral arms. The pattern is not fixed. It is not even a single, stable wave. It is more like the surface of a river in a breeze, always spiral-like, never the same spiral twice, generated continuously from below by physics that never quite rests. So the full picture, the honest and complete picture, is that there is not one mechanism behind spiral arms, but at least two, operating in different galaxies and possibly in the same galaxy at different times. Clean, long-lived grand design arms in galaxies like M51, driven by tidal companions or perhaps by a strong central bar, are well described by the Lin-Shu density wave. The woolly, fragmentary, constantly churning arms in flocculent galaxies are better described by transient, recurrent instabilities and self-propagating star formation, and many real galaxies probably combine elements of both. The science is honest about this. The textbook traffic jam picture is true and useful and beautiful, and it does not tell the whole story. And real scientists will tell you that themselves. There is another engine worth pausing on because we have talked about tidal companions as one way to drive a density wave pattern, but there is another driver, one that lives at the very center of the galaxy itself, and it is one that our own Milky Way possesses. Not all spiral galaxies are the same kind of spiral. Some are ordinary spirals, arms emerging directly from a round or oval central bulge. But others have something different at their core, an elongated bar of stars stretched across the nucleus, with the spiral arms beginning not at the center, but at the ends of the bar. These are barred spirals, and they are, it turns out, extremely common. Something like 2/3 of all disk galaxies with clear spiral structure appear to have a bar of some kind. Our own Milky Way is among them. Our galaxy is classified as type SBBC. That classification is a compressed description, S for spiral, B for barred, and BC for a middle position on the scale of how tightly wound the arms are. The bar at the center of the Milky Way is enormous. It stretches roughly 27,000 light-years from end to end, which is, interestingly, very nearly the same as the distance from the Sun to the galactic center. The bar is not a small feature, it is a major structural component of the galaxy, a thick, dense, rotating spindle of stars sitting at the heart of the disk. And that bar does something. It is not merely decorative. Bars drive gas from the outer parts of the disk inward along their length, feeding the central regions. They create gravitational disturbances that can stir and organize the disk. And perhaps most relevantly here, they can act as an engine that drives and maintains the spiral pattern in the disk beyond their ends. The bar rotates, and its rotation creates a rhythmic gravitational influence that extends outward into the disk and can help excite and sustain the density wave in the arms. The bar is, in this sense, a kind of timepiece set into the heart of the galaxy, ticking out a slow rhythm that the arms respond to. We know we live in a barred spiral, but knowing that and knowing where we live within it, that took most of the 20th century to work out, and the work is not entirely finished even now. Let's settle for a moment into our own address, because there is something quietly grounding about knowing where you are in the galaxy, not just in the abstract sense, not just somewhere in the disk of the Milky Way about halfway out, but specifically in the name structure on the particular lane, on the. The Milky Way has several major spiral arms. Two of the largest are the Scutum Centaurus arm, which begins near the end of the central bar on one side and sweeps outward, and the Perseus arm, which lies further out on the other side of the disk. These are the substantial arms, the ones that hold large populations of stars and gas and ongoing star formation, the ones that would appear in a photograph of the Milky Way taken from outside as the bright, curving ridges. And then there is the arm, or rather the spur, where we actually live. The Sun sits in a structure called the Orion Arm, or sometimes the Orion Spur. It is smaller than the major arms. It is, in the language of galactic cartography, an interarm spur, a shorter, less prominent feature lying between the Sagittarius arm on one side and the Perseus arm on the other. We are not in a grand spiral arm, we are in a spur, a side street if the major arms are the main boulevards. There is something I find oddly comforting about that. We are not in the thick of the galactic drama, we are not inside one of the great compression zones, the places of most intense star formation and ultraviolet glare. We are between the lanes, in a quieter region. The Orion Arm has star formation happening in it. The Orion Nebula is right here, not far in galactic terms. But we are not in the densest, most active part of the disk. We are in a moderately calm interarm neighborhood between the Sagittarius Arm curving around us on one side and the Perseus Arm lying a few thousand light-years away on the other, with the great Scutum Centaurus Arm sweeping further out. You are right now, wherever you are in the world, lying on the surface of a planet that is inside a spur of a barred spiral galaxy, between two of its major arms, orbiting a star that takes about 225 to 250 million years to complete one circuit of the galactic center. The galaxy's bar stretches across the center in a long spindle, nearly as long as the distance from us to that center. The arms beyond are density waves lit by the blue fires of newly born stars that die before they can escape. And this whole structure, arms, bar, disk, has been slowly, continuously turning and flowing for roughly 10 billion years. That is your address, and it is, when you sit with it, a rather beautiful one. But here is something important to understand, and it is one of those places where the honest science is slightly more complicated than the clean story. We have been speaking of density waves and pattern speeds and the correlation radius, as if these things are measured with great precision, as if we know exactly how fast the Milky Way's arms are rotating, exactly where the correlation circle falls in our own galaxy. And the truth is that we do not know these things as precisely as we might like. Estimates of the Milky Way's pattern speed, the speed at which the density wave rotates, have varied between different studies and different methods. The correlation radius, the ring where the stars and the wave move at the same speed, is somewhere in the middle disk, but pinning it down with confidence has proven genuinely difficult. Part of the difficulty is simply that we are inside the galaxy. Looking out at a distant galaxy like M51, we can take a photograph and see the whole structure spread out before us. We can measure the rotation at different radii by observing the Doppler shift of the light, how the wavelength stretches as stars move away from us and compresses as they approach. We can see the arms in their entirety and reason about their structure from the outside. But we are embedded in the Milky Way. We are looking at the galaxy from inside it. We are, to use a rather ordinary metaphor, trying to understand the shape of the building we are living in by looking out the windows. We can see our immediate neighborhood in great detail, but the overall structure has to be inferred from partial views, from careful measurements of distance and velocity, from radio observations that can penetrate the dust that visible light cannot cross, from infrared telescopes and the catalogues of hundreds of millions of individual stars. Recent decades have brought extraordinary improvements in these measurements. The Gaia Space Observatory, launched by the European Space Agency, has mapped the positions and motions of more than 1 billion stars in the Milky Way with a precision that was simply unimaginable a generation ago. And that data has sharpened our picture considerably, but there are still open questions. The exact pattern speed of the Milky Way's arms, and even whether the bar and the spiral have the same pattern speed or different ones, is still a matter of active research. Astronomers are still measuring the rhythm. The galaxy is still yielding its secrets slowly on its own timetable. There is something I find deeply reassuring about that. The honest admission that we are still figuring this out. That the science is alive and in motion, not closed off in a drawer. That the questions are real and the answers are not yet fully settled. A spiral galaxy that has been turning for billions of years does not reveal all its workings in a single afternoon of observation. It takes time to understand something that ancient, and it takes humility to say, here is what we know, here is what we suspect, and here is what we are still working on. The picture that has emerged slowly and with effort is this. Some spiral galaxies, the grand design ones, the M51s and their kin, maintain their arms through large-scale density waves sustained by a tidal companion or a strong bar, moving at a pattern speed that is steady enough to persist for billions of years. Others, the flocculents, the woolly and patchy ones, build and rebuild their arms continuously through local instabilities and self-propagating star formation sheared by differential rotation into short curved arcs that dissolve and reform. And many galaxies probably do both at different scales, at different radii, at different moments in their lives. The universe does not insist on a single mechanism. It is opportunistic. It uses what works. What all of these galaxies share, what the grand design and the flocculent and the barred and the ordinary all share, is the fundamental truth that the spiral pattern is not a fixed thing. It is not spokes painted on a wheel. It is not a set of stars that have been sitting in formation since the galaxy formed and will sit there forever. The pattern is dynamic. The pattern is a process. And in many cases, especially in the flocculent galaxies, it is almost more accurate to say the spiral is continuously created than to say it is maintained. The galaxy does not hold on to a spiral arm the way you might hold on to a branch. It generates one the way a river generates a ripple, continuously from the conditions, from the physics, from the ongoing motion of matter, through a system that has not yet come to rest. And now let's step back even further. Let's rise in our imagination to a place far above the disk, far above the plane of the Milky Way, to some impossible vantage point from which we could look down on the whole galaxy spread out below us, the bar at the center glowing, the arms sweeping outward in their long curves, lit by the blue and pink of star-forming regions. The inter-arm space is darker, quieter, filled with older, red and yellow stars drifting between the waves, the whole disk turning slowly, not as a rigid wheel, but in that differential way, the inner parts completing their circles faster, the outer parts taking longer, each star threading its own unhurried path through the pattern. What would you see if you could watch it over millions of years, played back in some accelerated dream? You would see the stars moving, you would see gas flowing into the arms, brightening them, then flowing out again. You would see the brilliant blue sparks of new stars flaring up along the compression fronts, and then fading, reddening, drifting away. You would see the arms themselves, not dissolving, not winding up into a blur, but persisting, glowing, the pattern holding its shape even as everything inside it changes, the wave moving through the water, the traffic jam remaining while the cars pass through. And if you watched long enough in that impossible, accelerated dream, you might even see the pattern shift. An arm fading slightly here, a new spur forming there, the galaxy breathing in slow motion, the spiral always spiral-like, but never quite the same shape twice. That is the galaxy. That is how it keeps its shape. Not by being still, not by holding its stars in fixed positions, but by being a pattern that is larger than any of the material that expresses it, a pattern that the material merely passes through, like a wave that the water only rises into and falls away from, while the wave itself travels on. And here is the thing about that, the thing I keep coming back to as we near the end of tonight's journey. That is not just a fact about galaxies. It is a particular kind of fact. It is the kind of fact that, once you have understood it, changes the way you think about permanence, about what it means for something to last. We tend to imagine that the things which endure are the things which stay still. A stone lasts because it sits there. A mountain lasts because it does not move. The universe, we might vaguely imagine, is most permanent where it is most fixed. But the spiral galaxy tells a different story. It says some of the most enduring structures in the universe are made entirely of motion. They persist not despite the fact that everything in them is flowing, but because of it. The arm endures because stars flow through it. The traffic jam exists because the cars keep coming. Take away the flow and the pattern dissolves. The permanence is made of the impermanence. And when you sit with that, when you let it settle, something interesting happens to the feeling of change itself. We often experience change as a kind of loss, the sense that something which was one way is now another, and what it was is gone. But a spiral arm is 4 billion years old, and it has never contained the same stars twice. Every star that lit it has moved on. Every gas cloud that was compressed in it has either collapsed into stars or drifted away. The arm is not diminished by this. It is constituted by it. The change is not happening to the structure. The change is the structure. The flow is not undoing it. The flow is what it is. You are not so different from that. The atoms in your body right now, with the oxygen in your blood, the calcium in your bones, the carbon in the long chains of your DNA, they have not always been yours. They came from food and water and air, assembled, by the slow chemistry of life into the particular arrangement that is you, and in time they will disassemble again and go on to be other things. The you that is lying here tonight is a pattern, the way an arm is a pattern, a shape that the material flows into and out of. And the fact that the material flows does not make the pattern less real. It makes it precisely as real as it is. There is also the question of the stars themselves. The ones born in those spiral arms, compressed from gas clouds into nuclear furnaces by the passing of a density wave. Those stars formed from hydrogen and helium. But inside them, over millions or billions of years, nuclear fusion has been building heavier elements, carbon, oxygen, nitrogen, iron, and all the rest. When massive stars end their lives, in supernovae, in those extraordinary explosions that scatter the products of a stellar lifetime outward into the surrounding space, they return those elements to the galaxy. They seed the interstellar medium with the atoms of complexity. Those atoms drift. They accumulate in gas clouds. Those clouds drift into density waves. The waves compress them. New stars form with new planetary systems, with new planets made of rock and iron and all those seeded heavy elements. And on at least one of those planets, some of that material arranged itself after a few billion years into something that can lie in the dark and wonder where it came from. You came from a star. More accurately, you came from many stars long dead, whose material was cycled through the galaxy multiple times before it found its way into the solar nebula that collapsed to form the Sun and the Earth, and eventually across all the slow work of evolution, you. The iron in your blood was forged in a stellar core and scattered in a supernova. The calcium in your teeth, the oxygen you breathe, the carbon in every cell of your body, all of it at some point passed through a stellar furnace, was scattered into the interstellar medium, drifted through the galaxy, was perhaps compressed in a spiral arms density wave, and found its way here. You are, in a literal and not metaphorical sense, part of the same flow, part of the same cycling of matter through pattern and dissolution and reformation that makes the arms of the galaxy glow. The universe has been doing this for 10 billion years, building patterns from flow, dissolving them, building new ones. And one of the things it built after all that time and all that cycling is a conscious pattern that can look up and recognize the process. That is, if you will forgive me for saying so, rather extraordinary. We started tonight, or I suppose it might be deep into tonight now, or perhaps early morning where you are. We started with a question that seems simple and turns out to be bottomless. How does a spiral galaxy keep its shape? And we drifted slowly through the answer, the differential rotation, the winding problem, the paradox that the arms should have wound themselves into oblivion hundreds of millions of years ago, and yet there they are, curving and glowing in galaxies that are older than the Earth. The resolution, C.C. Lin and Frank Shu, 1964, the density wave. The arm is a pattern. The stars flow through it. The traffic jam stays while the cars change. The wave moves across the water while the water only bobs. We learned why the arms glow, actually not because they are dense, not because they hold most of the mass, but because they hold the newborns. The brilliant, short-lived, profligate O-type and B-type stars that burn so brightly and so briefly that they die before they can leave the arm where they were born, lighting that arm in blue and wreathing it in pink hydrogen clouds, HI regions, from within. The arm is bright because it is a nursery, and because the nursery is always being resupplied, or always more gas arriving, always more compression, always more stars being born, the light persists. Even though every individual star that makes up the glow will be gone within a few million years. Even though the arm it was born in never contained those particular stars before. and will not contain them for long. We visited M51, the whirlpool, and its companion NGC 5195, whose tidal gravity helps sculpt and sustain the clean grand design arms. We considered the barred spirals, ours among them, the Milky Way's central bar stretching 27,000 light-years, driving gas inward, sustaining the pattern. We found our own address in the galaxy, the Orion Arm, the Orion Spur, the quieter inter-arm neighborhood between the Sagittarius Arm and the Perseus Arm, with the great Scutum Centaurus Arm sweeping on beyond. Not in the thick of a major arm, between the lanes, a relatively calm address, as galactic addresses go. We held the honest complexity of the picture, density waves for the clean grand design spirals, transient recurrent instabilities for the woolly flocculents, and a great deal of ongoing measurement and research still being done, pattern speed still being refined, corrotation radii still being mapped, the Gaia Observatory giving us 1 billion stellar positions and motions to work with, the science still alive and still asking questions. And we landed on the thing the galaxy has quietly been teaching us all along, that permanence is not made of stillness, that the most enduring structures are not the ones that refuse to change, but the ones that are built from change itself. That a thing can last for billions of years by being, in every moment, a pattern that the world flows through. That is a good thought to carry into sleep. The galaxy will still be turning when you wake up. The arms will still be glowing, lit by stars being born right now, in this moment, in the compression zones of density waves that have been traveling slowly through the disk since long before our sun existed. The Orion Arm will still be here, between the Sagittarius and the Perseus, our small and quiet inter-arm neighborhood. And the sun will have moved, not by much, not in one night, but a fraction of that long arc around the galactic center, continuing the orbit it has been on for 4.5 billion years. You have learned something real tonight, even if you were half asleep for most of it. Something that the galaxy itself demonstrates, written in the curves of light, across intergalactic distances. The wave is not the water, the arm is not the stars, the pattern is not the material, and things can last for an almost unimaginable span of time, by flowing rather than by stopping. That is true of galaxies. It is perhaps true of other things as well. If you enjoyed this slow journey through the disk of the galaxy, if any part of it reached you through the drowsiness and settled somewhere pleasant, a quiet like or subscribe would mean a great deal to this little channel. Small creators like me really do rely on your support to keep making these. It costs you nothing and it helps more than you might think. And do leave a comment. If you find yourself awake enough to type a few words, where are you listening from tonight? And what time is it in your corner of the world? I love knowing where these slow journeys end up. Which time zones, which beds, which night skies. Someone in the southern hemisphere might be able to see the Milky Way overhead right now. Someone in a city might have the lamp still on. Someone might have fallen asleep 2 hours ago and be reading this on a second listen. Wherever you are, I am glad you were here for this. The spiral of the Milky Way is turning outside, above you. So far away, it has never felt closer. The arms are glowing. The stars are flowing through them. Something is being born in the compression zone of a density wave, in a gas cloud that has never before collapsed, becoming a star for the first time. Close the books, dim the lamp, class is over, sleepy scholar.